Hi everyone, my name is Nathaniel Islas. I'll be presenting the Burrowing Owl Classification project I worked on this summer at the Engineers for Exploration. A little bit about myself. I'm a senior at California State University East Bay studying computer science and statistics. So how did this project start? The Engineers for Exploration's scientific collaborators at the San Diego Zoo wanted to better study the western burrowing owl because the local population is rapidly declining and at risk of going extinct in San Diego County due to habitat loss. The plan they devised to monitor and study these owls was to set up camera traps near owl burrows around San Diego. To the right is an actual picture captured by a camera trap. The owls inhabit burrows that are mainly dug by ground squirrels as well as prairie dogs and even tortoises. So, how are we contributing to their efforts? The problem that the researchers encountered is that the camera traps work as designed to capture an image at any sign of movement. However, this results in a large amount of images that are not necessarily of interest to the researchers since they don't have owls in them. Last year, E4E started working on a solution to this problem by developing a machine learning pipeline to automatically label the camera trap images. This summer, I worked on the system in which the researchers could easily interact with to have their data labeled. The project lead, Justin, wanted the system to be simple to use with little input required of the user. Essentially, the system would prompt the user to input the folder's file path that contains their data. Each file would then be fed through the machine learning pipeline, and the images that have an owl are organized in a new filtered images folder, along with a CSV of the prediction results for each image. There are a few steps in the pipeline to detect the presence of an owl in an image. The first is that the folder of images is sent to a detection model that provides the coordinates of bounding boxes around objects of interest. In the second picture, we see what one of those bounding boxes looks like around the two owls. This step increases the accuracy of the owl classification model. The second step crops an image to create a sub-image to be analyzed by the owl classification model. The third step analyzes the sub-image passed to the classification model. If the cropped image is predicted as being an owl, then the entire image is classified as owl. If there are multiple cropped images for an image and at least one owl, we predict owl for the overall image. Here we have an example of the system's output. We see the main filtered images directly on the left, which contains two subdirectories that I tested the system with. The subdirectories are organized according to the file name of the original folder processed by the system. Each subdirectory contains images, the model predicted the presence of an owl, and a CSV with the prediction results for all images in a folder. On the right is an example of the prediction results for a folder. It contains information on the file name, whether or not there was an owl, and the minimum number of owls detected. Overall, I was successful in creating a system that was easy to use and that will hopefully be of much help to our scientific collaborators. That is all for my presentation. Thank you so much, and a special thanks to Dr. Kastner, Dr. Schrugers, and my project lead, Justin.